Welcome to this last talk of today, and I have the pleasure to introduce my young colleague, Liang-Liang Xie, who is seen as one of the founders of network information theory. In fact, the very famous paper of Xie and Kumar, he's the first part of that paper. So, and he's going to talk to us about omnidirectional relay in wireless networks.
Thank you, Ravi, for the nice introduction. I also would like to thank the organizers for inviting me here. It is really a pleasure. Today I'm going to talk about a coding scheme which we call it omnidirectional relay in wireless networks. Before I start talking about the coding scheme, probably it's a better idea first let me make it clear what kind of wireless network model I'm studying. Because people with different background will consider different models. And the wireless network model I'm considering is a so-called additive white Gaussian noise model, AWGN model. So it is modeling the wireless network as a physical layer. So any node J, it receives a signal Y, which depends on the signal transmitted by all the other nodes, plus some white Gaussian noise. Here is a weighted summation of the signal transmitted by all the other nodes. The weights is the channel gain. So it's the channel gain from transmitter I to node J. And this noise is a white Gaussian noise with the mean 0 and the variance n. And we assume power constraint on all the transmitters. So each transmitter has a power constraint Pi. They may have a different power constraint. So this is the additive white Gaussian noise model. So by this model, basically we are modeling the network at the signal level. So you see each node receives the signal transmitted by all the other nodes. And the simplest situation is the case of two nodes. One node wants to send information to the other node. This is the corresponding additive white Gaussian noise model. And if we ask the question, what is the maximum communication rate? Node 1 can send to node 2, and the answer is given by Shannon. So this is the Shannon formula, famous Shannon formula. And it's the logarithm of 1 plus this guy. This is the signal to noise ratio at node 2. If we look at here, so P1 is the transmit power of node 1. And H12 is the channel gain from node 1 to node 2. Or we also can call it signal attenuation. So after signal attenuation, so this product basically is the received power at node 2.
Factor half?
I'm sorry?
1/2?
Oh, you mean here's 1/2?
Yeah.
Oh, if you consider complex model instead of a real model, okay. So you see, what really matters to the achievable rate is received power, not transmitted power. And the meaning of this is we can communicate at any rate less than this value reliably, but we can never communicate at any rate above this value. Well, if we consider a little bit more complicated situation, suppose there is another pair of nodes communicating at the same time, then we will see interference. So the signal received by node 2 will also be affected by the signal sent by node 3. And this normally we call interference. And if we treat this interference as noise and apply Shannon's formula, then we have this achievable rate. So you see the signal power from the node 3 will have the same role as the noise. And well, of course, you can achieve this rate, but if you know a little bit about network information theory, we know that we can do better than this. But how much better? And today I'm going to tell you a result which shows that it is possible to build completely interference-free wireless networks. So the final result will appear that as if there is no interference at all in the network. Well, that's not generally true. It's only true for special situations. I must first admit that. In what situations we can build completely interference-free wireless networks? This here is a situation. If consider this problem, we call it all source all cast problem. Suppose each node is an independent source, and it wants to send the same message to all the other nodes at rate Ri. So it's all cast problem, but it's not sending independent different messages to the other nodes. It's sending the same message to all the other nodes. It is an all cast problem, and each node is an independent source. So if there are n nodes in the network, so there are n sources. And now if we ask the same question Shannon has asked, so what are the maximum achievable rates? Because now there are n sources, so we need to consider n rates. And because they are in the same network, they are interconnected with each other. So we cannot consider them separately, because we want to achieve them simultaneously. So because of the interconnection, if we increase some of them, we may have to decrease some the others. So the question is, what are the maximum achievable rate vector? And here is an obvious upper bound. If we just apply Shannon's formula, this upper bound is obvious. You cannot do better than this. So this upper bound is for node j. So consider any node j. So this on the left-hand side, this is the total rate node j need to receive, because node j need to receive the message from all the other nodes. So it's a sum rate of all the sources, which is not itself. And on the right-hand side, what's this? This is Shannon formula. It's just here the signal power is the total signal power this node can receive from all the other nodes. This bound is obviously true. We cannot do better than this. Well, here we assume we don't use beamforming. Okay, we don't use beamforming. If you use beamforming, it is possible you have a coherent transmission, so that the two signals can add up constructively, so the signal power received can be boosted. But assume no beamforming is used, then the power just add up like this. If no beamforming, of course, we cannot do better than this. And what I'm going to show at the end of the talk is that actually this not only upper bound, it is also achievable. We can achieve this rate vector for this wireless network, for this all source all cast problem. And well, if you look at this, obviously there are two things you need to do in order to achieve this. The first thing is there shouldn't be any interference in the network. If there is interference, as we've seen before, you treat it as noise, then it would come to the denominator. But we don't see anything besides the noise itself in the denominator. So there shouldn't be any interference. And not only that, each node should also exploit all the signals transmitted by all the other nodes, because it is using the total power transmitted by all the other nodes. Okay, so how to accomplish these two seems impossible task. Well, the coding scheme, the title of our talk, the coding scheme is omnidirectional relay. So this scheme, I'm going to explain this. This scheme is such a scheme which can achieve that, can accomplish those two tasks. So what is omnidirectional relay? Now you may become more curious about this coding scheme. Well, actually, it's quite a long story. It started more than 40 years ago. The original work was by Liang-Liang in his PhD thesis. So consider the situation, the problem where node 1 wants to send a message to node 3. Maybe this distance is too long, but there is a node in between which can help. So what node 1 can do is it first send a message to node 2, and then node 2 forward it to node 3. So by 2 hops. But we know that due to wireless communication, the signal transmitted by node 1 will also arrive at node 3. Although node 1 sent this signal to node 2, it was not intended for node 3. And what Liang-Liang showed was actually this signal is useful for node 3. You can make use of it because this is not interference because it carries the information from the original source. But how much useful was finally proved by Kowa and Elgamo about 10 years later, and to show that for this network, and if you exploit this signal, and this is the best you can do as well as this, and that is you can achieve any rate less than these two logarithms. Let's see the first one. The first one is the logarithm of 1 plus this. So this is also a Shannon formula, and this is the power. This is signal power node 2 received from node 1. So from 1 to 2. So this bound basically makes sure that node 2 can decode the message sent by node 1. And what's this? This is the signal power node 3 received from node 1. And this is signal power node 3 received from signal 2. And we sum them together. So this is the total signal power node 3 received from both node 1 and node 2. And this makes sure that node 3 can decode the original message. So Kowa and Elgamo shows that any rate less than this 2 is achievable. This
Somebody got their cell phone on?
Yeah.
There's still
we found out who it was. Okay, continue.
There's still some interference.
Yeah.
Yeah.
Okay. So at first sight, you may think, oh, this is intuitively appealing. It may not be so hard to prove. But actually, if you think a little bit more about this network, you'll find it's kind of strange, actually, you can achieve this. Because if you look at node 3, well, it receives both the signals. You think, okay, you make use of both of these signals. But actually, these two signals, they carry different messages. And when node 2 is sending this signal, actually, at the same time, node 1 is sending a message which which is new to node 2. So these two signals, actually, they are carrying different messages, although they are carrying the messages from the same source. Node 2 can only send a signal which carries the message it has decoded. But node 1 must send a signal which carries a message which node 2 hasn't decoded. Otherwise, it's not useful for node 2. So actually, there is a synchronization problem here. And actually, there's a time delay here. So these two signals, because these two signals, they are not carrying the same message, how can we simply add them up together? They are not for the same decoding. Well, indeed, the scheme to achieve this is non-trivial. Kowa and Elgamo developed a so-called block Markov coding to achieve this. So consider time horizon. They divide the time horizon into multiple blocks. And because there is a time difference, so in block 1, when node 1 is transmitting the first message, actually node 2 has nothing to transmit because it hasn't received any information from node 1 yet. And now in block 2, node 1 proceeds to transmit the second message, W2. And now node 2 can transmit W1. Suppose at the end of the first block, node 2 already decoded W1. This is ensured due to this inequality. Okay, so as time moves on, node 1 is always one step before node 2. So they are not synchronized. So for the decoding at node 3, what happens is it needs to make use of these two blocks in order to decode W1. Because in both these two blocks, there are signals for W1. Okay, so from the first block, node 1 is transmitting W1. So this is the contribution from node 1 to node 3. So from 1 to 3, the total signal power received from node 1. And in the second block, only node 2 is transmitting W1. And node 2 is transmitting something new, and which node 3 cannot decode at the end of this block. It cannot decode yet at the end of this block. So if something you cannot decode, actually it will cause interference. So if you look at the contribution from the second block, you will see this is the signal power from node 2. But the signal power from node 1, that is this part, goes into the denominator. So it is indeed causing interference. But what's interesting is if you add these two together, because there is log, so it becomes product, and this n moves up, and it will cancel this part. So if you add these two together, what you will get is this. So the final result is as if you make use of both the signal power from node 1 and node 2, and there is no interference at all. That was what we intended to prove. So that's kind of a strange, but Kowa and Elgamo showed that this is the case. And well, mathematically, what was hard in the proof was to show that you indeed can add these two together. So the summation is true. So information theoretically, this is the hard part. You can sum them together. So after you decode in W1, then you can delete it. Then you can move on to decode W2. And the situation becomes the same as before. So this process can be continued. So a short conclusion we can draw here is what's the use of block Markov coding? The use of it is block Markov coding can cancel out interference resulted from delay. And after that, there have been many attempts to extend this result to the case of multiple relays. And finally, we know that it can be generalized. And there is no interference, and all the signal powers are exploited. And for any node J, it can make use of all the signals transmitted by the nodes upstream. Well, this extension is non-trivial though, because the original coding scheme in Kowa Gamo's paper need to be modified. Okay, but you see there are many signals, but I haven't considered any signals in this direction, in the reverse direction. Why I haven't considered those signals is because there is a unique information flow in this network. So the information flow in this direction. And so the upstream nodes will receive the information, receive the message before the downstream nodes. And so what the downstream nodes will transmit are totally predictable. So the signals sent by the downstream nodes, this red line, is predictable to the nodes upstream. So they can be canceled. So we don't need to worry about those signals. Well, so far we considered case of one source in the network. You may think, okay, that may not be surprising because anyway, there is only one source in the network. All the signals are basically for that source. But what if there are multiple sources? Will still be possible to achieve no interference? Is it still possible to achieve no interference? And seems there will be contention and competition between multiple sources. Well, we start from a most simple situation, simple example. Consider the case of two-way relay. There are two sources, node 1 and node 3. They are both sources. They want to communicate with each other. And there is still a node in between which can relay the messages. Now, will there be contention in this network due to these two sources? First, in order for node 2 to decode these two messages, in order to then help to relay the messages, we need these three inequalities. So these three inequalities are basically the multiple access region in network information theory. You see here, there's no interference, and all the signals are exploited. Okay. This we know already. This is achievable according to the basic network information theory, which was developed a long time ago. Now for node 3, if we insist that there's still no interference and all the signals are fully exploited, then we are saying, okay, this inequality is enough for node 3 to decode R1. So this is signal to noise ratio. If we look at here, this is the signal power from node 1, this signal power from node 2. So suppose node 3 can fully exploit both these two signals. And the same for node 1. We want node 1 to exploit both the signals from node 2 and node 3. Okay, So that is according to our guidance that there is no interference. All the signals are fully exploited. So then we write down these 5 inequalities. Now the question, is this achievable? And there's some conflict here. You see, basically, this is the this power comes from the signal transmitted by node 2. And where node 1 wants to fully exploit this signal power. And the same signal, node 3 also wants to fully exploit it. Is that possible? Because node 2 can only send 1 signal, but it needs to transmit 2 different messages with this signal. And it needs to be fully exploited by both the destinations. So both node 1 and node 3 needs to fully exploit the power sent by node 2. And although they are interested in different messages. I'm just to rephrase this question we need to answer. Well, does this remind you something? Well, if you know a little bit about network coding, here's something you may find familiar to this problem. And Amina, yesterday, she talked about, also mentioned this this network coding framework in her talk. Okay, so actually, this is the idea of network coding. Actually, we can do this. You consider this two-way relay network. But now, we are not at the physical layer. Let's jump to the network layer. Let's consider the bits. Okay. Suppose node 1 wants to send bit B1 to node 3, and node 3 wants to send bit B3 to node 1. Okay. So what node 2 can do is, instead of transmitting these 2 bits separately, actually it can combine them using the XOR operation. It only needs to send 1 bit. And the good thing is, node 1 already has B1, then it can do this XOR operation to recover B3. And node 3 already has B3. It can do this same operation to recover B1. So both the destinations are satisfied. So it looks as if by sending just 1 bit, node 2 successfully transmitting 2 different bits. So this is basic idea of network coding. Now I'm going to look at this operation from another perspective, in another way. This is so-called binning. B1, B3, they together, there are totally 4 possibilities: 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1. And now I'm going to throw this 0, 0 and 1, 1 into the same bin. And this 1, 0 and 1, 0 and 0, 1 into the same bin. So if this 2 happens, I will transmit this bin. If this 2 happens, I will transmit this bin. Okay. And well, that's just another way to look at this operation. They are totally equivalent. Why I want to look at this XOR operation in this way is because it can be more general. So generally, if you look at the message, it can have many possibilities, and this can also have many possibilities, and they may not have the same number of possibilities. So this may not be a square. But still, you can do this binning technique, and you create enough number of bins, and then you can throw them in. You can use some deterministic method or use random binning. And if you do this, then this is the binning technique. And then especially in the Gaussian case, well, you actually don't need to do binning because in the Gaussian case, you can create enough number of code words because you have a continuous alphabet. Then this binning is not really necessary. But the idea is, if you use this binning technique, basically it's the idea of network coding. You can you apply it to this two-way relay network, but this is at the signal level, at the physical layer. Okay, and you can show that this is indeed achievable. So indeed, you can both node 1 and node 3 can exploit the signal power completely transmitted by node 2. It's as if by node 2 sending one signal, but it's fully used for each of them. Well, if you can do two-way relay, then of course you can consider more ways. Okay, three-way, if you have a 3 messages to transmit, you can also do this. If you can consider 3-way relay, then, well, generally you can consider any number of ways of relay. And so by sending one signal, basically, you can transmit multiple messages in all directions. So why not call it omnidirectional relay? Well, so a short summary. So what is omnidirectional relay? So basically, there are only 2 components. One is block Markov coding. That is because of a relay, because of the time delay. We do need that. The other is binning, because you have multiple messages to forward. So somehow you need to bing them together in order to forward all of them just by sending one signal. Well, now the question is, okay, so you developed a coding scheme. So the basic idea is clear. Now, how good is this omnidirectional relay? Or more specifically, for what kind of networks will it be good? Well, we cannot expect it is always good for general networks. So now question, so what kind of networks it will be good? And so from now on, I am going to talk about networking. Before all coding part, it's actually to information theories, those are easy part. It's too easy maybe. But now on, this is hard part. This starting now, it becomes hard. Okay. So the first network problem we want to consider is the all source all class problem. I have already mentioned before. Why we want to start with this problem? Because this is probably the situation where the omnidirectional array will function the best, because you are considering all cast problem. So basically, the message needs to go to every node in the network. So that's probably the situation where the omnidirectional relay will be the best candidate. Okay, so let's first consider this problem. Let's see how good this omnidirectional relay will be. Well, we need to be a little bit specific. So what kind of omnidirectional relay scheme for this all source all class problem? So remember, there are only 2 components: block Markov coding and binning. So we need to divide the time horizon into blocks. In the first block, if you look at any node, it transmits its own message of this block. And it also needs to decode the message sent by its neighborhood. Let's call it one-hop labels. So NJ1. So this one denotes it's one hop labor. Okay. So what's one hop labor? Well, it's not very clear yet. Okay. Maybe we can think of those labors which I can decode their message directly. Let's call it one hop labor. In principle, everybody is one hop, yes, because they are all connected because signal. But the problem is maybe some nodes are too far away. You cannot decode the message sent by those nodes, although you can receive the signal sent by those nodes. The cooperation is not in yet. The cooperation will happen in later blocks when the message comes along the way. But just in first block, you cannot reach the whole network. You can only reach a small neighborhood. So let's call it the one hop labor. So then in the second block, what happens is this node J, it still needs to send its own message. But it also needs to help to relay the other messages. So it also needs to kind of forward the messages it's decoded from its labels. So it tries to help its one hop labels. So I use this bracket to denote binning, the binning idea. So because this node now has many messages, multiple messages to send, so it binds them together using one signal to send them. And at the end of block 2, it still decodes the messages of its one hop labels of the current block. But it also wants to reach further, for the 2 hop labels. So, but now it's not trying to decode the message of those nodes of the current block. Actually, it's from the previous block. So it tries to decode its 2 hop labels message of the previous block. So there is a time delay here, as we have seen in the relay, the simple relay network. And so this basically is the idea. You can continue this process as the blocks move on. You want to reach the whole network until basically the messages from nodes very far away will be forwarded to you eventually. But now the question is, as we said in the beginning of our talk, is this inequality sufficient to ensure that you can reach out to the whole network? You can basically collect the messages from all the nodes. And actually, it's not so easy. We only have one inequality, and that's not sufficient. In order to make sure this routing works, this tree structure, so the message by 1 hop, by 2 hops, by 3 hops, it finally reaches this destination. Basically, we need, according to network information theory, we need 2 to the power n-1 inequalities. That's basically the idea of multiple access, because for each node, there are n-1 sources it has to decode. So we need to check 2 to the power n-1 inequalities. That's too complicated. And in networks, due to topology, due to signal attenuation, and so on, it's too complicated to calculate. And we don't want to do that. We want to get something simple and insightful. But now we only have one inequality instead of 2 to the power n-1 inequalities. So what can we do? Well, there is a very interesting result. I call it a key Teklich lemma. This is very interesting. So in order to make sure this tree work, we need 2 to the power n minus 1 inequalities. But instead we only have this one. Actually, this is the last one of all those inequalities, the last one. But just based on this one alone, we cannot say anything. We cannot say this tree will work, this routing will work. But what we can say based on this is, node J can always decode something. I will explain it. What does this mean? Node J can always decode something. It's not completely useless if we don't know the other inequalities. And maybe the other inequalities hold, maybe they don't hold. But doesn't matter. As long as this inequality holds, node J can always decode something. Well, in order to explain that result, actually it's not difficult to understand at all if you know a little bit about network information theory. Actually, it's very simple proof, but maybe people haven't think about what happens under that one inequality yet. So this is a basic result from network information theory, probably the most basic result from network information theory. And what it says is that if there are multiple sources trying to communicate to the same destination, in order to make sure all the communications, all these rates are achievable, we need these inequalities. We need to consider all the subsets of the sources, all subsets of sources. If there are n sources, then there are basically 2 to the power n inequalities we need to consider. So this is called the multiple access region. And this condition is both necessary and sufficient condition. We do need all of them to hold in order to make sure this node can decode all the sources. And if one of them violates, then we cannot decode all the sources. But there is no such result in the textbook which tell you what will happen if you only know about the last inequality. So here is the situation we have. If we only know about the last inequality, then S equals n. So if we only know about this inequality, what will happen? Well, we can find out by ourselves if it's not in the textbook. The result is that node J can always decode a long empty subset of n, treating the others as interference. I just don't know which long empty subset, but I know there are always some subset which is long empty, and the sources from that set I can decode. The other sources I cannot decode, but it's fine. They will cause interference, but it's fine. But this subset I can decode. Okay, this is actually very simple to prove. Now, our situation basically is a multiple access. The only difference is just the multi-block multiple access, because we are considering multi-blocks. And but nevertheless, this conclusion can be extended to the case of multi-block multiple access. So that's what I mean by node J can always decode something. Okay. But still, we are not sure if will this routing work, because we only know, okay, something will happen, but we don't know what will happen. So I'm trying to be aggressive. I'm trying to use a greedy operation of the omnidirectional relay scheme. Actually, this omnidirectional relay scheme, it has many flexibility in it. So each node, actually, it can choose to which messages to decode and which messages to forward. It's not necessary for it to forward all the messages. But here, because we have that lemma there, because something can always be decoded, so let's be aggressive. Let each node try to decode messages as many as possible, and try to forward the messages as many as possible. So that's what I mean by the greedy operation of omnidirectional relay. So what we are sure is each node can always decode something. Okay, so maybe in the first block, this node J can decode something, decode the messages from these two. And in the second block, this tree will grow. It will cover a larger area, and so on, until this tree reaches the whole network. So the bottom line is this omnidirectional relay scheme will work as long as this tree will grow to cover the whole network. Then we are done. Then we are sure all the messages will, this node will decode all the messages sent by all the sources. And there is a difference here from what we tried to plan before. Over there, we try to grow a tree. We were thinking, okay, we want this kind of routing. It grows like this way. So first, which is the first hop labels, which are the second hop labels. But here, instead of doing that, we just let the tree grow by itself. That gives us kind of the flexibility, that adaptability.
This basically comes down to the telescoping property of the capacity from the directions.
Yeah.
So I mean, it's only a one-line proof, so why not give it?
Well, it's not hard, so easy yet. Okay, you will see. Actually, there are still some tricky things.
No, but just in terms of the lemma, at least, it's not. That's one-line proof.
Yeah. Yes. In terms of lemma, but here actually. You may think the tree will eventually grow to cover the whole network because we have this lemma. But actually, it's not like that. Because this lemma says each node can always decode something. But it may not decode something outside. Okay, so let me backward a little bit. We want this tree to grow to cover the whole network. Because we're using the greedy scheme, so whatever this node decoded will basically forward it to this destination. So, so this node questions, will this node decode something outside or not? If it can decode something outside, then it will surely reach this destination. That's according to that greedy operation. But the problem is, we hope it grows like this. But the problem is, it's not so easy, because our lemma only says each node can always decode something. So this node maybe decoded something sent by this node. Okay, that is also decode something. It's not decoding something outside of this tree. Okay. So things are not so easy or so optimistic as we have thought. So this is what we hope. We hope the tree will eventually grow like this. So how to make sure that tree will grow to cover the whole network? Here is the main theorem. So basically, this is a cut-set bond. It has a cut-set bond interpretation. So if you consider this network, you cut it, consider any card. Then you have a set S and the complement set, S complement. And this theorem basically says that from this complement set, you can always find a node. Maybe this one, because this is closest to the set S. You can always find a node, J. If you consider the communication from this set to this node J alone, forget about the other nodes, then this is the bound. This is the cut set bound. So node J needs to receive all the information from this set. This is the sum rate from that set. And this is the total power transmitted by that set, and which is received by node J. So this is the Shannon formula. It has the Shannon formula interpretation. So this node J must be able to do that. So if this holds for any card in this network, then basically the idea is this tree will grow. It will reach out. If you cut anywhere, it will not stop inside. It will reach out. Okay. Well, remember our goal was we want to prove this inequality is enough. Okay. And what we finally being able to show was this. And they are actually different. This only corresponds to the case where we only consider those S with one node in S complement, not all the S. Okay. So we haven't been able to meet our goal completely, but in the case of networks with kind of evenly distributed nodes, and the powers are all the same, and the rates are all the same, kind of balanced network. Actually, we can show that our goal was met in the sense of those inequalities are basically the tightest. We can forget about the other S. And obviously, the result really depends on the network topology. For example, for this network, if you have two clusters of nodes which are separated far away from each other, you cannot expect that you can forget about this gap, because we are basically considering the decode forward scheme and how the information can pass through this gap. That's not possible. Okay, so this result actually, in summary, it only works for a network which are balanced, equally distributed nodes with equally distributed nodes. And we can extend the result to general discrete memories network models. Okay, I guess I don't need to talk too much about this. These two information theoretic, and we can have similar results, similar theorems. And this may be interesting to mention. We can consider time-varying operation of the scheme. So then we can consider half-duplex modes for wireless communication. Before, we only consider full duplex, so each node can transmit and receive at the same time. But if that's not possible, if we are only able to do half-duplex mode, then we can also apply this result. And this is the corresponding rate. Okay, so a quick summary. So basically, I first introduced the idea of omnidirectional relay. It has these two components, and it has these two features. All signals are exploited, no interference at all. And we applied it to the all source all cast problem, and we found that it is good for evenly distributed network. It is good in the sense of it is optimal. It is exactly optimal if there is no no beam forming. Okay. Okay. Thank you. Yes.
In the case you allow, sorry, in the case you allow for a signal cooperation,
Yeah.
then you have to substitute in all your bounds the hij square with a singular value
Right.
of the matrix. Do you have any idea, in that case, how far you are from
Yeah. It's
the optimal?
so if you can use beam forming, right? You basically you have a coherent signal combining. Then basically the power will be square root and then summation and then square. And that at most will double, because if you take the square out of the logarithm, you will see a constant 2 before that logarithm. So that will at most double what we can achieve here. So even by using beam forming, the best result is double the rate we can achieve here. That's just a constant gain. Actually, I wouldn't think we are able to do that if the channels will have like random phase distribution each, because if you are beam forming in this direction, you won't be able to beam form in the other directions. So basically, if you get some gain, because we have that bond, okay. Because we have this bond applied to all the nodes. So if by beam forming you increase the power received at this node, then basically you won't be able to do this for the other nodes. So the power received at the other nodes won't be able to be boosted. So generally, I don't think beam forming, even with beam forming, you can do much better than this.
But you may be able to boost the receiver which has the least SNR.
Yeah, but okay, that's right. If you boost the receiver which has the least SNR, well, in the best situation, even if you assume you can boost all the receivers, the gain is at most double. Yeah, that's right.
Any further question?
Yes.
Well, you alluded to results which go beyond the Gaussian case. So, what is the main result in this setting?
Beyond the Gaussian case.
Yeah.
You mean for the general channel model?
Right.
Yeah.
So, you have the same result extended.
Yeah, it's the same result. Yeah, it's kind of same kind of inequalities, same kind of bond. It's like a parallel to the result in the Gaussian case. So, but yeah, we can with this. I think a more general model we can put a fading, consider fading into the model, and we can consider half duplex mode. Yes.
Just a remark about the beamforming. I think if you consider very low power, then you can gain much more than double. If the power per node is very small. If you do beamforming, then you gain.
Okay, if you use beamforming, if you consider much low power, okay, so you are suggesting because of the square root will basically increase the value of p. If p is very small, so square root will actually increase it, but that won't increase much. Yeah, even if in that situation you won't be able to increase it much, because you see this is logarithm that yeah, at most you double it. Probably the gain is better even in the high power case where you you will be able to see a square outside. Yeah, I don't think that's so clear yet. Yeah, okay.
Question.
Is it the same case as if we are using superposition coding and use the interference canceller? So will we be able to achieve the same rate?
Oh, okay, superposition coding. Oh, that's, yeah, maybe I can mention a little bit about that. So by superposition coding, okay, the good thing with superposition coding is now you are not using one signal to transmit multiple messages. If you do that, then you can basically do beamforming, because now you don't need to consider multiple messages at the same time. Okay, so this is also was also in Cole Algamo's paper. But if you do beamforming, the bad thing is, if you do superposition coding, the bad thing is node 2 need to share its total power to different messages. So that's the loss. If you do beamforming, node 2 can no longer use its total power for both of them. So that's the loss. And of course, you can develop a general result for superposition coding, but it's really messy compared to this network coding scheme. Because here, at least it's very, at the coding level, it's very simple. The inequalities are very simple.
Okay. I guess no further questions. Thank you very much.